Hi, I want to ask you a very simple question. If you go to a store and buy some fruit, here are some apples and oranges. And for apple, each of them would weigh 100 grams. And they are identical because we are talking about physics. Don't challenge me on that. For oranges, it is 75 grams. Okay, I just make it up. And again, they are both 75 grams exactly. Now, what you do is you try to think about, hey, so the total weight, if you try to add them up together, it will simply be, well, 350 grams. Okay, and so yeah, that's probably enough for you to take in a day maybe. So you decided to buy it. And now what you do is, of course, you have to put them into a bag, for containing them all together. And so the plastic bag actually will weigh nothing. Of course, this is hypothetical, so it's literally 0 grams. So now the question is, if you try to compare their mass, all right, if you have a balance like that, how would they look like when they are on the balance? Would they be heavier on one side or would they be balanced? Let me give you 10 seconds. Okay, let me tell you the answer. If you are doing this in the normal daily life, and if you're really buying apples and oranges and try to weigh them like that, the answer, of course, they will balance, no matter you use the plastic wrap or try to weigh them separately. However, in physics, if these are not really apples and oranges, if these are proton and neutron. So for example, if the apple is actually proton, the oranges are actually neutron. And if you really try to weigh them one by one on the left hand side like this, so one neutron, one proton, one neutron, weigh them one by one, versus if they are put together as in a nucleus. So here we've got 2 proton and 2 neutron, and obviously this is helium, all right? Helium nucleus. If you remember, the number is 4,2. That means 4 mass number and 2 proton number. So yeah, that is helium nucleus. Interestingly, according to what scientists find out, for helium nucleus, they actually would have slightly less mass. And this is a big question for us because we have been believing conservation of mass for so long. So what exactly happened? This is very counterintuitive. In order to understand this strange observation, we first have to learn a few things. The first thing is called the unified atomic mass unit. And because normally when we try to describe mass in physics, the SI unit we use is going to be in kg. However, kg is a really large scale of unit when we try to describe, for example, one atom or even one proton or one neutron. And therefore, for convenience, physicists has invented a new unit for mass, and it is called U. And the full name is obviously atomic mass unit. And the best way of doing it is probably just picking one element that is abundant enough for us to have in the world, which is carbon 12, which has 6 proton and 6 neutron and also 6 electron. And so in this case, we just simply, by definition, there's really not a strong logical reason behind, to be honest, 1/12 of it. And so kind of the average of 1 proton or 1 neutron, because you have 12 nucleons in total. So this unified atomic mass will be that many of kg, and this value can be found on data booklet as well. Alright, so now let's try to do an example on this. Pause the video now and try it yourself.
A few moments later.
Alright, so this should be a very simple example, and what you have to do is just to express the mass of proton, neutron and electron, which were the information in kg to the unit of U, the atomic unified mass. And so allow me to be lazy here. What you have to do simply is just to divide this with the number that you have got from the data booklet. In fact, in the data booklet, you can see here now, they also provide you electron, proton, neutron mass in U. So technically you've got the answer already, but here is just an exercise for you to do. So what you can think of is 1 U equal to that many kg, and so here if you try to use the dimensional analysis, what you've got is kg, and if 1 U equal to that many kg, then what you can do is to divide it by this number. So 1.661 times 10 to the power of negative 27, and so in that case, this whole number, will be in U already. Okay, so that will be the same for the other two as well. So don't try to copy the data booklet answer, try to really press a calculator and find it out. Okay, finally I've finished pressing the calculator. So these are my answer, and let me just double check it with the data booklet. So wait a second. Did I press anything wrong? Why is this smaller? Wait, so strange. 1.6726231. What happened? So strange. Okay, this is wrong. 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay. Yeah, so strange. So wait, it is still wrong? Oh my god. But very close. Yeah, this is very close. 1.66, 1.006 or 7. 1.007. Okay, and then this is 1.0083. Wow, that's so strange. Maybe because of the number that I used initially here, 1.661 is not really good. I mean, the question told me to take 6 decimal places, but then the value I used for 1 U is 1.661, so only 4 sig figs, so that's why it produced an error, I believe. For electron, okay, pretty close enough. So yeah, I think methodologically, this is how you can do, right, when you try to convert that into U. Oh, so the textbook actually provided you with a longer, like more precise value of 1 U. So if you use this one, I think the one that you get, right, if you look at how they do, is going to be closer to the data booklet. Yeah, it is actually exactly the same as the one that you find on data booklet. So yeah, you need to use this one. So, and also I think now you understand why we care about the precision a lot. Back to chapter 1, how many sig fig you can take depending on your raw data. So now you can see a bad example from me. Now let's dive into the tiny world using the unified atomic mass unit. So going back to our previous question, the missing mass was a terrible big question for us because we believe conservation of mass for many years in science, and if it is not true, then it's going to ruin and destroy our whole physics system. Luckily, we have got Albert Einstein, who is smart enough to understand the missing mass is something to do with the energy, because when you try to put the nucleons, proton and neutron together or separate, it involves force, because there will be attractive force or repulsion force between them, and that means it also involves energy. And so in fact the missing mass would be equivalent to the new energy that's been released in the reaction, and therefore there is a new equation called E equal to MC², probably the most famous physics equation ever. Although the idea of having the missing mass converted into the energy is literally a crazy idea, the application of this equation is actually very simple. So let me show you how. E is simply the energy that you are going to release, which is called the binding energy, and M is the missing mass that you find, which is again the mass defect more precisely. So you could also see as delta M, so the mass changes. C is the speed of light, which is a constant, and we just have to substitute into this equation. The definition of the mass defect can be found here. So again, it is simply saying the mass of the proton plus the mass of the neutron separately is going to be larger than the one that is putting together as nucleus. So the difference is known as mass defect. So you may want to copy down this somewhere on your notes as well. Now let's start with our baby step on this simple question. Try to find out the mass defect of the gold nucleus. Pause the video and try it yourself.
A few moments later.
The whole question is very simple. The only tricky part that you should notice is whether the question is referring to nucleus or the atom. Of course, if you're referring to atom, then it includes everything, proton, neutron, and electron. And if you are only talking about nucleus or nuclear, that means it is only referring to proton and neutron, and there's no electron mass included. So here, what you have to do is simply taking the whole thing minus the proton number. As you know, 79 is a proton number, which we will substitute later on, and the neutron number is 197 minus 79, and then we are going to multiply the neutron number later on. So for proton number, we can find in the data booklet, okay, this one 1.007, okay, my memory is really bad, 276. And then for neutron 1.08665, 1.00. Okay, and so just press your calculator and you will find 1.673274. Okay, this is the whole thing I find with negative, and it's normal because, as we said, when you separate them, it actually will get greater mass than the one that put together. So that's why you get negative. In fact, I should do it in the other way around, using the proton and neutron mass separately minus the whole thing. Okay, but then I guess it doesn't really matter here. You can just convert it back to a positive value. So for better presentation, I can say delta M is this one, and so the mass defect could be the positive value, so 1.673274 U. Alright, if you're okay with the mass defect, then we can move on to binding energy. So as we said, we use the equation E equal to MC² to calculate the energy. And so this is an expression that is specified into this. So binding energy equal to mass defect times C². However, when you try to think about substituting the numbers into it, you should find out, hey, it's a bit strange because the unit for the mass defect we got is in U, unified atomic mass. But then C, speed of light, is in a unit of SI unit, so meter per second. And so what will happen to the binding energy unit then? And of course, that wouldn't be joule because these are not in SI unit. So it becomes quite tricky and inconvenient in a way. And that is why if we try to think about for 1 U, 1 atomic mass unit times the speed of light square, then we can actually convert it back to kg and then times the speed of light square, and eventually we can get the energy in joule. So this is a value that is very, very small, as you can see, 10 to the power of negative 10 joule for 1 U, if you can convert that many mass defect into energy. And so we can consider using another energy unit we have used before, which is called the EV, electron volt. And so using that, we can find out 1 U can be equivalent to the energy of about 931.5 mega EV. So this is something that you will be able to find in the data booklet as well. And that explains why there's another term. When you have 1 U equal to that many kg, with which is very tiny amount, it should also equal to 931.5 mega EV C negative 2, because this one you have already considered the speed of light already. So that's why you have to, the unit itself has to divide the speed of light square so that this whole thing is in the dimension of mass. So it's just the unit itself. If you try to look at the dimension, you should also be able to derive these mass energy equivalent also. So in example 7.8, here is also another example to show you how you can find the energy equivalent of proton, neutron, and electron. So you can just pause the video and have a look quickly. To summarize what you have learned in this video, I would like you to try this last example with me together. Okay, so this example is talking about there's a fusion reaction, nuclear fusion. In fact, the equation that you have been learning, E equal to MC², can be applied to nuclear fission and nuclear fusion as well. So maybe later on we'll have more exercise in the next coming video. But here, this is example of fusion. So you are combining things together. So it is saying for a star, you have some hydrogen nucleus, and then it will combine into helium and something like this here. So it includes a helium nucleus. So again, very important, you have to pay attention, it is nucleus, not atom. And so there's no electrons involved, right, in this nucleus. And also 2 positron. Positron is the antimatter, right, which is something that we will talk more in the future of the electron. So for everything in the world, for first instance, as far as we know, there's always antimatter of that particular particle. So for example, for proton, there's something called antiproton. For neutron, there's also something called anti-neutron. So for everything, there's also an anti-version of it. So positron is an anti-version of the electron. And we'll talk more about something special between them. Here we've got 2 electron neutrino. And again, neutrino is something that people lately find. If you remember in the previous video, we talked about the beta plus and beta minus decay. They will either emit neutrino or anti-neutrino. For this one, in this question, we are going to take the mass to be nearly 0. And in fact, they are really nearly 0, but not exactly equal to 0. So we will talk more about it again in the future. But for this one, we can take it as 0 for now. For photon, this is clearly, no matter this question or even outside of this question, the mass is literally 0, because you have learned about photon is just EM wave, right, actually. So mass is 0. So I think we are all good for now. They have provided us the mass of the helium to be this one. I believe this one should be in the atom. So that's why you will have to minus the electron later on. Alright, I'm double checking on Google. So helium atomic mass is really 4.0. Yeah, it's the same number as this one. I think, well, the question itself is not really good enough. They should really specify this is helium atom or helium nucleus. Otherwise, it will be quite confusing. So anyway, here the one that we find means that the number that we've got here include the electron. So now let's find the change of mass between before the reaction and after the reaction. So before that, you have got the hydrogen nucleus, and hydrogen is simply proton if you think about it, because this is the simplest atom that you can find, which you only have one proton and nothing else. For hydrogen atom, yes, of course, there's electron outside, but then we are talking about nucleus, so only proton. So that means you simply have 4 times the proton mass, which is 7276, 1.00, okay, U over here, and then minus the one that you have on the right hand side, or maybe I can express, yeah, let's just keep it like this, right? If you don't mind, I'll just keep it the whole thing. So we've got the helium, but then if you think about, again, this mass include electron. So in theory, we have to minus the electron, because in the equation here is it already said it's nucleus only. So we should minus the mass of the electron times the 2. Because for a usual helium atom, you got 2 proton, and therefore you should have 2 electron, right? So that's why you need to minus the electron to get the mass of the nucleus. However, because here we've got positron, okay, and if you remember just now, I said positron is the antimatter of electron, and so what you are going to do is you're going to plus the mass of the positron, and in fact, for all the antimatter, the mass is going to be the same as the regular matter. So electron mass and positron mass is going to be the same. And so what we are going to do is to add, because these are on the right hand side, 2 electron mass or positron mass, and that actually means they will cancel out, right? Because you add 2 and minus 2. And for the last 2 items, neutrino and photon, neutrino in this question we will also treat as 0 because it's really small, right? Which is not going to affect almost anything. And also for photon is massless, so I think that's all for us. So eventually you should get the mass difference to be 0.026504 U. Okay, and that will be the mass defect that you find. Alright, and so lastly, what you can do is simply by using E equal to MC², finally using this equation. One way is you can convert the mass defect in U into kg, and so the whole thing can be substituted into M and also times the C², and you can find the energy in joule. That's one way. However, we normally would not express it in joule. Instead, we'll express it in dV, electron volt. So what you can do instead here is try to get the mass, which is the one that you find, but then you can multiply that with the one you find on the data booklet. As we mentioned, 1 U is going to be 931.5. Okay, maybe I can write the unit here also, so it's easier for you to follow, because you just learned this newly. Mega EV, and don't forget there's a C-2, right, in this unit when you try to convert it to the so-called energy equivalent. And in the equation there is a C². So this is the whole idea of why we will have to get the C-2 here. Or you can also say that, hey, because mega EV or EV itself is an energy unit, so it doesn't make sense to say energy equal to mass. It doesn't really is. So yeah, so that's why we have to add the C-2, because that's how you can derive it. You can look at how we did earlier. And so eventually, of course, this will get cancelled out, and then this actually is should have U per U, right? This is how many mega EV C negative 2 per 1 U. So this unit, this U, and this U will cancel out because they multiply together. And so that's why eventually your answer, energy, is simply this number times this number in mega EV, the remaining unit. That should be 24.688476 mega EV. So taking the sig fig, I think we can take 24.69 mega EV. So in this video, you have learned about the unified atomic mass unit and also understand the interesting mass defect in the nuclear reaction, how to calculate the binding energy using mass defect with the equation E equal MC², and also applying the idea of mass and energy equivalent to see how 1 U can be converted into 931.5 mega EV. And in the coming video, we'll learn more about several examples. I'll see you again in the next video. Bye.